In this video, I'll show you how to use notation to help you think about Riemann sums using the context of a Mars rover. The Opportunity Mars rover is powered by solar cells to move around the surface of Mars. The rover is currently moving along a 100-kilometer path. As it travels, the rover kicks up dust, which accumulates on its solar cells. The amount of dust that it kicks up depends on the composition of the surface it is traveling over. A rockier surface kicks up less dust than a sandy surface. The goal for the scientists is to figure out how much dust will accumulate on the rover's solar panels. To do this, we use Riemann sums. In particular, we want to compute left and right Riemann sums, and write these using sigma notation. To do this, we first divide the rover's trip into equally sized intervals. In this case, each interval is 20 kilometers long. We'll look at our data that shows the rover's position along the path and the rate of dust accumulation. And we'll add a column to note the length of each time interval. We'll write p for the rover's position along the path and r of p for the rate of accumulation at position p. So, for example, r of 0 is 6 milligrams per kilometer, r of 20 is 3.5, and so on. Then the amount of dust that accumulates over each interval is approximately the rate for that interval times delta p. We can compute these products for each interval. So, for example, we'd travel 20 kilometers at 6 milligrams per kilometer for the first interval, which gives us 120 milligrams of dust. We can do this computation for each of the intervals and then add these up to compute the total amount of dust that has accumulated. When we were doing these computations, we were using the rate at the beginning of each interval, so we were creating a left-hand Riemann sum. Let's use function in sigma notation to write this sum. For the first interval, we multiplied the rate at the beginning of the interval by the length of the interval. For the second interval, we multiplied the rate at 20 kilometers by the change in position. And we continue to do this for all of the intervals. We write the symbol sigma to show that we're adding these up, and the things that we're adding up are r of p times delta p. And we figured out that this is all equal to 310 milligrams. It's important to note here that we didn't use the rate at the 100-kilometer mark. We only took the rates at the beginning of each of the intervals. We could also use the rate at the end of each interval to do our calculation. For example, for the first interval, we'd multiply 20 kilometers by 3.5 milligrams per kilometer to get a total of 70 milligrams of dust. We could do this calculation for each interval and then add these up to get a total of 210 milligrams. This would give us a right-hand Riemann sum, which we would write using similar notation as our left sum, except the rates would come from the end of each interval. Now, this seems a little odd. If you look at these two sums, they use exactly the same notation. However, in the first case, you'd get 310 milligrams, and you'd get 210 milligrams in the second case. If you just saw this notation, how do you know which number is correct? Clearly, our current notation for Riemann sums isn't sufficient to distinguish between the right and left-hand sums, so we need some notation that will help us figure out what's going on. Let's start over here. We know that the total accumulation can be approximated by a left Riemann sum. Now, I'm going to introduce some labeling on our depiction of the rover's trip. I'm going to label the 0-kilometer mark as p sub 0 to distinguish it from the other values of p. Then I'll write p sub 1 to indicate the 20-kilometer mark, and so on. Now, when we're computing a left Riemann sum, for the first interval, we would evaluate the rate at p sub 0 and multiply by delta p. Then for the second interval, we would evaluate the rate at p sub 1 and multiply by delta p. Then repeat for the third interval using p sub 2. Again for the fourth interval using the left endpoint, p sub 3. And then for the last interval using p sub 4. Now, how do we write this all using the sigma notation? We'll use the letter k to indicate the value of the subscript. So for the first term in this sum, k would equal 0. For the second term, k would equal 1, and would continue with the rest of the terms. So if we write this sum using sigma notation, in each term we're multiplying r of p sub k by delta p, and the values of k start at 0 and end at 4. We indicate this by writing 0 below and 4 above the summation symbol. And we already computed that this is equal to 310 milligrams. We can also approximate the total accumulation using a right-hand Riemann sum. We'll use the same process as with the left-hand sum, but we'll use the right endpoints instead. For the first interval, we'd find the rate at the 20-kilometer mark, which we labeled as p sub 1. For the second interval, we compute the rate at p sub 2. Then at p sub 3 for the third interval, p sub 4 for the next interval, and p sub 5 for the last interval. If we use k to indicate the value of the subscript, then this first term corresponds to k equals 1, the second term corresponds to k equals 2, and so on. Using sigma notation, we're evaluating the rate at p sub k and multiplying by delta p, but this time we're starting at k equals 1 and going up to k equals 5, which we indicate by writing these values below and above the summation symbol. And we previously calculated that this is equal to 210 milligrams. In summary, we have labeled the endpoints of each interval using a subscript. In the left-hand sum, the subscripts start at 0 and go up to the next to last subscript. In the right-hand sum, the subscripts start at 1 and go up to the last one. So now we have a way to write Riemann sums that distinguishes between the left and right-hand sums.